Dr. Hans Kaper and Dr. Hans Engler are both professors in the Department of Mathematics and Statistics at Georgetown University in DC. They've written a book on a topic of wide interest today, mathematics and climate. Their book explains how mathematical and statistical tools can be used to understand the dynamics of the Earth's climate system. The book recently won the Atmospheric Science Librarians International Choice Award for 2013 as the best book in the fields of meteorology, climatology, or atmospheric sciences. Congratulations, Dr. Kaper and Dr. Engler, and welcome. This is exciting, and this is our first ever Google Hangout interview.
Let me start. My first question is, how does math help us understand geophysical and chemical processes in the Earth's atmosphere and oceans, thus helping us better understand climate? Dr. Kaper?
Sure. So mathematicians can concentrate on sort of the fundamental phenomena that occur in our climate system. We cannot predict or study everything that's going on in the system, but we can focus on certain issues like, for example, why are there glacial cycles? Why have there been ice ages? We can ask questions like, what happens to the overturning circulation in the ocean, in the northern Atlantic? There are mathematical models that we can study, and on the basis of that, usually dynamical systems theory, we can explain why certain phenomena happen, what are the critical elements in a change when a change occurs, and that's how mathematics in general can contribute to our understanding of the workings of our climate system. You may want to say something about statistics.
Yeah, I'd like to also add the fundamental processes in the atmosphere and in the oceans, that is, the parts of the planet that influence climate as we experience it, like fluid flow and heat transport and things like that, have been described successfully by mathematical equations for a long time. For about 150 years, these equations have been known and have been studied, although there are still many open questions. So there's a broad set of tools which can be brought to bear. And of course, an additional aspect is that climate is something that we experience over a long time that is sort of an average or typical patterns, something that has a statistical feature to it. And again, statistics is a part of the mathematical sciences that is very well equipped to study and extricate patterns and trends and other things of interest.
That's great to know. Lauren.
Our second question is, what is the role of math in helping us curb the challenges we face due to human influence and to global climate changes?
Well, maybe I'll go first, and we should probably both have something about this.
Sure.
Curbing or influencing or changing the way that humans are influencing the climate system, of course, is a task that has many, many different aspects. Policy, it's a political choice, economic aspects. Mathematics can often help us understand possible consequences of actions that we do or that we fail to do. For example, it's possible to predict perhaps a range of possible changes in the storm intensity, assuming that certain actions are done or not. And that has, again, implications for the way that people live and work in certain parts of the world. So mathematicians can predict scenarios, different scenarios, and therefore provide tools for decision makers and for the general public to decide on what to do.
I don't have much to add. It is indeed exploring what-if scenarios, right? Once you have a mathematical model of, say, a climate system, you can play with it, as it were. You can change things, mimicking what humans do to the atmosphere, and see what happens. You can turn up the knob, for example, release more CO2 in the atmosphere over the next few years, and see what happens 50 years from now. So it is a tool to explore climate scenarios. And the outcome of these experiments is then input for the decision makers, policy makers, who have to make choices. you can either do nothing or you can do something. And if you want to do something, what should be the optimal path? And that's what the contribution that mathematicians can make to the study of climate.
And that leads right into our next question. Can you give us like a brief overview of some of the mathematical and statistical techniques and tools that you present in your book, Mathematics and Climate?
So we can maybe go back and forth because there are at least half a dozen different topics which we can cover.
Sure.
Each chapter in the book essentially covers a particular tool. One of the purposes of the book was also to introduce people to methods of mathematics. So we use climate problems as motivators to teach mathematics, mathematical methods. You will see that in the book we devote quite a bit of attention to dynamical systems and bifurcation theory. Those are two big chapters in the book. In the beginning, after brief introductory chapters, dynamical systems is a technique, provide a technique for studying systems that change. And they explain the nature of change. And that's a very essential question, the central question essentially in climate studies. What happens if you change certain things? And dynamical systems theory and the theory of bifurcation phenomena that's closely related to it, they provide the tools for answering questions like what happens if something changes.
Perhaps as a specific example for a dynamic systems theory approach, we have a discussion there of a very simple but effective model for that explains phenomena such as global ocean currents, the Gulf Stream that transports heat from the subtropics to the northern latitudes and the Atlantic, and then there is a reciprocal stream that has to take the water back because it doesn't all pile up in the north, obviously, that goes through the deep parts of the ocean. Why is this stream going in this form? What could maybe slow it down or accelerate it or otherwise change it or maybe even stop it? And simple mathematical models, relatively simple, they are at the level of advanced undergraduate students, can shed substantial light on this and have actually been used by climate scientists and oceanographers to look for triggers and possible telltale signs of change. So mathematics can sort of point in certain directions and say, look at this. This is probably important. Another example that we have in the textbook is not related directly to ocean currents, but we have a simple model there that was first discussed by climate scientists in the 70s that can explain the temperature distribution on the globe as it is right now quite successfully in terms of some very few parameters, very few realistic parameters. You have maybe 3 or 5 different parameters, such as how much sunlight reaches the Earth and where are the polar caps, and all of a sudden you can pretty much explain the entire temperature distribution on the planet from north to south, with a few interesting exceptions, and that in turn leads to new questions. So mathematics very much can be part of the dialogue with climate science if it's done right.
Fantastic. What does this book aim to do that other similar books haven't yet? Or can you elaborate on any specific techniques or areas of the book that have not been covered in books similar to yours?
Certainly. So as I said, the book was written with 2 purposes in mind. First of all, introduce mathematics majors, maybe other scientists, to climate problems. And second, to use that as a motivator to teach them methods of mathematics and statistics. So in that sense, our book is unique. It covers, it's not only an introduction to climate science, but also an introduction to methods of mathematics and statistics. Also, the fact that we combine mathematics and statistics in one and the same book is unusual. Usually mathematicians study modeling using concrete physical phenomena, and statisticians have their own techniques. They're explained in the book, and that's how they learn it. Now they see the connection. In our opinion, you cannot do climate science without doing both mathematics and statistics. So it's critical that these two are brought together in the same book. That's an unusual feature. We've never seen that before. And I think another argument that I can give is that this is really the first time that a book about climate is addressed to mathematicians. Mathematicians have not really been interested in climate science. There hasn't been an interchange of ideas. And with this book, we hope that we can promote that.
That's great. But again, talking more about how mathematics and statistics help us understand climate science. I think one of the least understood aspects of climate research is how models are created, how climate models are created. And I know you cover conceptual models in your book. And I was wondering if there is, if you could shed some light on how these climate models simulate the Earth's environment, maybe to a layman, briefly.
Well, perhaps one should start at the extreme end, which is the most complex models that currently are being used in climate science. They will try to say something about the atmosphere, heat and moisture transport in the atmosphere, interaction with the ocean through rain and evaporation and storms, heat transport in the oceans in turn, maybe even interaction with the continents through rain and evaporation and all that. So it's extremely complex. We're cutting this down by more than one step to models, more than one model, which look at only one of these processes. For example, there's a class of conceptual models which we're discussing in the book, which is only a caricature of what's happening when you're heating an atmosphere. The atmosphere is not considered three-dimensional, but just two-dimensional. And then we're only looking at one particular kind of pattern that can possibly occur, which is essentially the pattern of a thermal updraft in one region, followed by a thermal downdraft somewhere else. This is not new. It's been done for about 50 years, and it's known as the Lorentz model. It's very successful in understanding certain fundamental physical processes. So instead of looking at, let's say, wind blowing over land and ocean and heat rising over the ocean at the beach, when you're in the summer, you have a breeze coming from the ocean because the heat rises over the land mass. And instead of having the cooling effect of water and all that coming together, you have a very, very simple phenomenon, just a two-dimensional atmosphere, as if it was a two-dimensional, not a three-dimensional layer of air surrounding us, and you have only one kind of type of breeze and only heating and no ocean and only land. Now, what can you still pull out of that? And it turns out you can still pull out quite a bit. And that's one example of a conceptual model. So you're ignoring a number of important things, but you're keeping some, and you are aware of the effect of that, of course, but you're keeping some other essential aspects in the mathematical model, and therefore you will be able to reproduce some phenomena which have their counterpart in the real world.
Okay, great. What was the main motivation for you to write this book? And do you hope this would inspire more research into one of the most challenging problems of our time?
I'll give a quick answer. For me, the main motivation was because Hans suggested it. I'll pass it to you.
So it was about 2008 that I became interested in climate issues. And as I said earlier, not too many mathematicians had looked at that. So being an applied mathematician, I'm always interested in looking for new mathematical problems, and I found this a very interesting area. So when I joined Georgetown University here, I made a suggestion that maybe we should teach a class on the subject. The best way to learn a new subject is by teaching it. So we got together and produced a class, and at the end of the class I thought, well, this is interesting. We had to do a lot of work together to pull all this material for the class in one syllabus, and maybe there's a broader audience for it. So let's start writing a book. And that's how it came about. So it's a combination of personal interest in climate issues, interest in finding interesting applications of mathematics, and then it happened, in this case, that there was a wide audience. We draw lots of students who were interested in figuring out what is going on in the climate. As we say in the preface, we've been conducting an uncontrolled experiment with the atmosphere, releasing CO2 in the atmosphere, not worrying about the consequences. Our Earth is finite. The amount of resources we have is finite. We better be careful with them. So all this came together, and fortunately, the interest in climate issues has been rising in the last few years. And as we can tell from the sales of the book, actually, quite a few people look at it and look at it with different eyes. And that is the whole purpose.
Right. And that's great. And we're really glad that you wrote this book, so more applied mathematicians and researchers are taking an interest in this. And now on to my next question. How do we get the public to take more interest in this? The problem, and I'm sure you know this, there's been such a resistance among the public, at least not the entire public, but a large portion of the public who does not totally either understand or even accept that there is human influence in climate change. And I was wondering what you thought was the role of mathematicians, applied mathematicians such as yourself, and the research community in general, climate scientists, in educating the public, and how can this best be done? As far as we know, climate science is really complicated, and for a wide population to understand that is that much more complicated. So what are your thoughts and insights on that?
You want to start?
Yeah, well, the communication of scientific results to the public and their implications, of course, there are people who are specializing in that. They're called science journalists. Mm-hmm. And so SIAM has people that do this for a profession. But of course, the broader scientific community, including in particular mathematicians, can play a role just by adding their voice to this discussion. One also has to acknowledge that there will be parts of the public which will never be convinced. So you cannot try to get everybody to follow the arguments which are currently being piled up and amassed by the scientific community that show that climate change is man-made and will have bad consequences. So in general, I would think that mathematicians in particular, just like with other, say, public policy questions where mathematics can shed a light on consequences of possible choices, should really become more involved in these discussions than perhaps they have been in the past. And there are exceptions, of course, people who have write articles, blogs, write articles for the New York Times, and their colleagues who are very active, including Hans, who wrote a blog for a year-long blog last year, or a Math on Planet Earth blog. So, so writing, talking, including perhaps topics from climate science, even into introductory mathematics classes, can play a role. Everybody can help a little bit, and it's also not just being a missionary or doing their share, but there are interesting and exciting teachable issues within the climate science and mathematics intersection, which can be used even to make things interesting for beginning students. I think that's where mathematicians also can play a role.
I don't have much to add, except that we just have to keep pushing. We have to keep making the argument that, yes, climate is a serious issue at this point. There is general consensus among the scientific community that most of the problems are man-made, caused by humans. And sure, there will be people who never believe this, but gradually the word will come through. We can start in our own community, the mathematics community, through a book. We go and give talks in general for a general audience. Anywhere we go, we should hammer it every time. This is an important problem. We better pay attention because we don't have much time.
Right.
There are serious reports that we can bring to the table, like the IPCC reports. They all come up with the same conclusion. Sure, we can ignore it, but then we're in trouble. And the sooner we start, the better. It is like the problem with smoking. 50 years ago, nobody cared about it. Gradually, the word came through that, hey, smoking is not so good for your health and not so good for society. The same with climate. We'll have to keep hammering on it, and eventually the policymakers, the decision makers will stand behind it, and hopefully we'll start doing something about it.
That is definitely a great analogy, because it did take a long time for the public to begin to understand the harmful effects of smoking, and hopefully the same will happen with climate science, climate change, as people begin to see some of the consequences. But you have certainly started the conversation really well with your book, and thanks a lot for joining us in this interview. And just for our viewers, the book, you can purchase it on the SIAM website. If you go to www.siam.org and click on books on the left navigation bar, you should be able to find the book Mathematics and Climate by Dr. Hans Kaper and Dr. Hans Engler. Thanks again, Dr. Kaper and Dr. Engler.
Thank you very much.
Thank you. You're welcome.